Welcome to Module 5. Module 5 is about electronic mail security. Under electronic mail security, we will be discussing Pretty Good Privacy and S-bar mail. So let us start Pretty Good Privacy. Pretty Good Privacy or PGP provides confidentiality and authentication services mainly that can be used for electronic mail and file storage application. This was developed by Phil Zimmermann, who selected the best available cryptographic algorithms as the building blocks of PGP. Zimmermann integrated these algorithms into a general purpose application that is independent of the operating system and processor, and that is based on a small set of easy to use commands. Zimmermann made the package and its documentation, including source code, freely available via the internet. They entered into an agreement with the company to provide a fully compatible low-cost commercial version of PGP. PGP is now available free worldwide in versions that run on a variety of platforms. The commercial version satisfies users who want a product that comes with vendor support. It is based on algorithms that have survived extensive public review and are considered extremely secure. It has a wide range of applicability. It was not developed by, nor is it controlled by any governmental or standards organization. It's now on an internet standards track. However, it still has an aura of an anti-establishment endeavor. These are the services provided by PGP. It provides us four services mainly: digital signature, message encryption, compression, and email compatibility. For digital signature, the algorithms used as DSS followed by SHA or RSA followed by SHA. For message encryption, they use CAST or IDEA or triple DES with Diffie-Hellman or RSA. So for compression they use zip, and for email compatibility they use radix 64 conversion. So I think you can read and understand the description part. When you say this, you want a digital signature to be achieved, you generate a hash code of the message using SHA-1 for example, and this message digest can be encrypted using DSS or RSA. These are signature schemes. So for DSS or RSA, they will use the sender's private key. When it is message encryption, a message is encrypted using CAST 128 or IDEA or triple DES, okay, with one-time session key generated by the sender. So you understand that there are two keys involved: a session key, two types of encryption actually, as symmetric encryption and a public encryption. So for symmetric encryption, you use a session key or a one-time key which must be distributed securely. You know, there is an issue of secure distribution of keys in case of symmetric encryption. So for that you can use Diffie-Hellman or RSA. You can use RSA where you encrypt your session key with the recipient's public key. Okay, so you are encrypting your session key to protect it. Then at the receiver side, receiver can decrypt it using his private key. Compression is using zip function. For email compatibility, most of the time email may not be in the ASCII format. Sometimes it can be binary data. So in such situations, it need to be converted to ASCII string, for which you use the radix 64 conversion. So let us try to understand all the functions in detail. PGP authentication for first one. PGP authentication uses a combination of SHA-1 and RSA. Because of the strength of RSA, the recipient is assured that only the processor of the matching private key can generate the signature. Because of the strength of SHA-1, the recipient is assured that no one else could generate a new message that matches the hash code. As an alternative, signature can be generated using DSS followed by SHA-1 also. There is an option of detached signature. Detached signature means a signature that is not attached with the message on which you are putting your signature. Okay. So this detached signature concept is useful when more than one people want to sign the same message. So this is also supported. When you want to provide confidentiality, you can encrypt your message. Mainly confidentiality is achieved using encryption. For encryption, you can use IDEA or triple DES. Although this is referred, you can use a symmetric key system to encrypt your message to provide confidentiality, and then the session key is transmitted with the message so that the receiver gets the same. same session key. This is like a one-time password. To protect the key, this session key is encrypted using the public key cryptographic system. As an alternative to RSA for key encryption, PGP can also use the Diffie-Hellman key exchange to transfer the session key. You can also provide confidentiality and authentication together. How will you do this? The sender first signs the message with private key. That is, you are ensuring, you are signing with your private key. That means you are ensuring authentication. Then you can encrypt the message with the session key. So when you encrypt, you are providing authentication. Finally, the session key is encrypted using the recipient's public key. The third service provided by PGP is compression. As a default, PGP compresses the message after applying the signature, but before encryption. They do not compress the signature, but they compress before encryption is applied, because this can save a lot of space. And this has computational advantage also. Encryption algorithm can work on a compressed message. The placement of compression algorithm is critical. Applying hash function and signature after the compression would constrain the PGP implementation to the same version of the compression algorithm. Message encryption is applied after compression to strengthen the cryptographic security also. So you get two advantages. The compression algorithm used is SIP. Email compatibility provided by PGP is explained here. Many electronic mail systems only permit use of blocks consisting of ASCII text. To accommodate this restriction, PGP provides a service of converting the raw 8-bit binary stream to a stream of printable ASCII characters. The scheme used for this purpose is Radix64. Each group of 3 octet of binary data is mapped into 4 ASCII characters, and this format also appends a CRC to detect transmission errors. Anyway, you understand that you are you are using Radix64 conversion to achieve ASCII conversion. So this figure explains how all the functionalities are achieved. Look at the first figure. That is achieving authentication only. So the sender creates a message. Okay, SHA-1 is used to generate a 160-bit hash code of the message. Okay. Next, the hash code is encrypted with RSA using sender's private key. Okay, EP stands for public key cryptography. PRA stands for private key. Now you are applying public key cryptography. You are encrypting the message using the private key of the sender. Now you are doing authentication, right? Now you are concatenating the message and code. It is zipped and sent to the receiver. Okay. At the receiver side, it is unzipped. The message is unzipped. Then you recompute the hash from the message. Also, the retrieved hash. Now the hash was encrypted using private key. Now the hash is decrypted. DP stands for public key decryption. Hash is decrypted using the public key of the receiver. Sorry, public key of the sender. Now you compare both the hashes and accept if they are the same. Next, for confidentiality, the sender generates a message and a random 128-bit number that can be used as a session key for the message. The message is encrypted using cast 128 or IDEA or triple DES with a session key. Understand? With a session key. Now, you can see EC is used here. EC stands for symmetric encryption. Understand? EP stands for public key encryption. DP stands for public key decryption. EC stands for symmetric encryption. DC stands for symmetric decryption. And KS stands for the session key. Okay. Now you are using symmetric encryption. You are using the session key KS. Now the session key KS must be sent securely to the receiver. For this, you can either use Diffie-Hellman, or I told you can also use public key cryptographic system. This figure uses a public key cryptographic system where they are taking KS and PUB. PUB is the public key of the receiver. Now it is encrypted using the public key of the receiver. KS is encrypted using the public key of the receiver. It is concatenated with the message and it is sent to the receiver. At the receiver side, you can see they are taking they are first decrypting the session key. Okay, look at DP. What is DP doing? DP is public key decryption. It uses the private key of the receiver and it decrypts the session key. Now with the session key, decrypted session key, see, session key is then the receiver uses RSA with his private key to decrypt and recover the session key. The session key is used then to decrypt the message you can see DC decrypts the message. Now if compression was not shown, so compression, you are compressing the message and you retrieve the message. Okay, I forgot to describe compression at the sender side. So compression is also performed. Now it is in figure C, you can see compression and confidentiality and authentication are tied together. Now look at this figure. So this figure explains the complete process. You take a file. If you need signature, you can generate a signature. If you do not need a signature, you can compress it. Then you are checking if confidentiality function is required. If that is required, you can apply the confidentiality function, which we explained already. If confidentiality is not required, you can do the convert to radix 64. So this is the generic transmission diagram. At the receiver side, you convert you do the conversion. If confidentiality is required, you do the decryption process. If it is not required, you will be doing the decompression, the reverse of what we did there. So this is about PGP or pretty good privacy.